All right, ladies and gentlemen, chemistry students, let's look at Chapter 11 review questions. We are going to walk through all of these together and answer them, do the calculations necessary. I may set up the problem and you might have to finish the calculation, but let's look at Chapter 11. And remember, Chapter 11 is all about gases and the gas laws here that show you the relationship between pressure, volume, temperature, and number of particles. That should be an N there, sorry, number of particles. Okay? So remember our ideal gas law, PV equals nRT. It rhymes, just say it over and over. P is your pressure, V is your volume, N is the number of moles, the number of particles, T is temperature, and R is our constant. R is the constant. Remember, temperature is always measured in Kelvin. N here is in moles. And then volume could be in liters, it could be in cubic meters or something like that, so that can vary. Pressure could be in atmospheres, it could be in torr or millimeters of mercury, it could be in Pascal. So depending on what units you use for pressure and volume, that will alter, and you'll use a different R value depending on what units you use for pressure and volume. And that is all found in the table for your R constants. Okay, that's just a quick review. And let's answer the questions. State the assumptions that the kinetic molecular theory makes about characteristics of gas particles. The main point here is kinetic molecular theory. The KMT is basically saying particles are in constant motion. Constant motion. Okay? That one statement helps us determine a lot about the properties and the characteristics of gases in particular, but also matter like liquids and solids. Okay? Now we could go into the other 5 assumptions there when we talk about gases, but we're just going to leave it there that particles are basically in constant motion. Okay? Number 2, why does a gas in a closed container exert pressure? Well, in a closed container, you basically are restricting the motion of the gas particles. And gas particles, remember, they're always in constant motion, and they are going to be moving in different directions as they expand and as they carry that energy with them, that kinetic energy. Well, if they're in a closed container, then they're going to be pushing against, they're going to be bombarding, they're going to be colliding with the inside of that container. And anytime there is a force on a particular area, that's going to exert pressure. So pressure is force over area. And so you can, in your own words, just describe what I mentioned, that the particles are exerting force against the inside of that container. Okay? Number 3, explain what is meant by the partial pressure of a gas within a mixture of gases. How do these partial pressures affect the other gases in the mixture? Okay, partial pressure basically is the pressure of an individual gas, the pressure that its particles are exerting. Okay? But there may be multiple gases in a container, in a mixture, like our atmosphere is made up of different gases. So partial pressure is simply this: the total pressure that is in a container due to all the gases in there, or the atmospheric pressure, the pressure that we feel on our bodies, that is going to be the sum of all the pressures of the individual gases. So pressure 1 plus pressure 2 plus pressure 3, and etc., depending on how many different gases you have. Okay? So the total here, okay, if your total pressure is a certain amount, then each gas is going to exert a certain amount in order to add up to the total. The individual gases are not going to have to exert the total pressure. They all add up together. Okay, they all add up together. The individual gases, the partial pressures of those individual gases give you the total pressure. Number 4, explain why pressure increases as the gas is compressed into a smaller volume. So this is showing you pressure and volume relationship. Pressure and volume. So why does the pressure increase as you compress it into a smaller volume? Well, what happens is, as the volume decreases, the pressure is going to increase. Well, let's think again what pressure is. Pressure is force over area. If you take and you have a balloon, let's say, all right, and it has gas particles in there that are bouncing against the inside of the walls of that balloon, and then you exert more pressure on the outside. You increase the exterior pressure and you shrink that balloon. Now that balloon is going to be smaller, but the number of particles didn't change and the temperature didn't change. So now you have particles that are going to be hitting a smaller area, a smaller surface area. Here the surface area is quite large, or larger. Now it's going to be hitting a smaller surface area. The same particles colliding with the inside of the balloon at a smaller pressure or smaller surface area. Well, what happens when this area here decreases? The pressure goes up. When the bottom number of the denominator goes down, the overall ratio increases. Okay? All right. So kinetic molecular theory here. Let's talk about this law. So Guy Lusek's law here says the relationship between pressure and temperature, I believe. So that is equal to, that ratio is a constant. So let's talk about it in terms of kinetic molecular theory. As these particles are moving, kinetic molecular theory, always in motion, if the temperature increases, what's going to happen to the pressure that those particles are exerting? It's also going to increase. Why? If temperature is increasing, that's because the kinetic energy is increasing. And that's 1/2 mv squared. What does that mean? It means that the velocity is increased. Those gas particles, they're not going to change their mass, but they can change their velocity by adding more heat, adding energy to those particles. And that means the kinetic energy is going to increase, and therefore the temperature is going to increase. If they have an increased velocity, now they're going to, let's go back to our balloon, right? If you have particles that are going to increase their velocity, now they're hitting the inside of the walls of that balloon with greater force. Now the force is going to increase. Well, pressure is force over area. The force is going to get bigger. When this numerator gets larger, the pressure, the whole ratio increases. So that pressure is going to increase. If you slam these particles with greater force against the inside of the balloon, then there's going to be increased pressure. Now, I say balloon, I really should say this should be a container that does not expand. It's inflexible. So this pressure is going to increase. Let's say it's a glass sphere or glass tube or something like that. That pressure inside of the container is going to increase as you increase the temperature. If this was a flexible container, then it would expand. It would keep pushing it out, and the volume would change. But if it's not flexible, the pressure is going to increase, the greater you increase the temperature. Okay? Number 6, when using the ideal gas law, let's talk about that. PV equals nRT. It rhymes. Say it over and over. Okay? Why do you have to pay particular attention to the units used in the calculations? Well, that's because this R value is equal to PV, if I solve for this R, over NT. Remember, N is always moles. T is always Kelvin. But volume and pressure, we can use different units for that. So you have to be aware of which units you're using for pressure and volume in order to determine what the R value is going to be and what the units of the R value are going to be. Okay? So that's why we're careful of the units for pressure and volume. Just be aware of those because the R value will change. That constant will change. Okay? If you're using atmospheres for pressure, if pressure is going to be in atmospheres, and I think if volume is in liters, then this R value is going to equal 0.0821, I believe. Okay? And so that would be pressure, atmosphere, liters per mole Kelvin. It's kind of a weird unit, isn't it? But that's what it is. All right, diffusion. What is diffusion? It's real simple. Diffusion is mixing. It's just that simple. Okay. So, if you have ever seen a diffuser is something that takes and spreads out the particles so that they will kind of vaporize a little bit and spread out into the atmosphere. Okay, and then you can maybe have a diffuser for a nice smelling perfume or a scent that you want to spread out through the room, and that diffuser is going to help that particular whatever it is, that liquid, that volatile liquid, spread out into the atmosphere and evaporate quickly. Okay. All right. Let's see here. Ammonia and alcohol are released together across a room. Okay, so which will you smell first? All right, so basically what we want to do here is these are both going to evaporate, but which one is going to travel faster? Remember, the lighter particles are going to move faster. Why? Because they have a greater velocity in order to match the kinetic energy of the heavier ones. So if they're at the same temperature in the same room, they have the same temperature, both gases, both particles have the same average kinetic energy, but the lighter one is going to travel faster. The heavier one is going to travel more slowly. So you would have to figure out which one of these is heavier, which is lighter. So we just look on the periodic table, and nitrogen is 14, so NH3. Nitrogen is 14, the 3 hydrogens is 3. I add them up, I get a molar mass of 17. Carbon for C2H6, you probably see already that this one's going to be greater. Carbon is 12, so that's 2 times 12, plus the 6 hydrogens, plus the oxygen, which is 16, and you can already see that's going to be greater than 17. So it is the C2H6O, this alcohol, that is going to be heavier, so this is slower, and the NH3 is lighter, so this is faster. Okay? So which one you smell first? You'll smell the NH3 first. Alright, now we're going to get into some calculations. And I'm going to put this all in the context of either the ideal gas law, PV equals nRT, or I might write it as just the combined gas law, PV over T, okay, is equal to some constant. Alright, so here we go. The atmosphere can support a column of mercury 760 millimeters high at sea level. What height of liquid whose density is 1.4 times the density of mercury could the atmosphere support at sea level? Okay, so this is looking at, remember we have a barometer that basically is looking at how the mercury in this tube is getting pushed up. Remember, this is a thing of water here, it's a bowl of water. Atmosphere is pushing down in that water, and that water is pushing up on this tube, and in the tube you've got some mercury. So that mercury gets pushed up this tube, and the higher it goes, obviously, the greater the atmospheric pressure. Okay? So right now, the atmosphere can support a column of mercury 760 millimeters high. So this is from the water level up to the top of maybe the mercury. Maybe we measure that at 760 millimeters, something like that. Okay? What height of a liquid whose density is 1.4 times the density of mercury could the atmosphere support at sea level? So if the density is 1.4 times, it's not going to be able to go quite as high. All right? So if we take this 760 and we divide by 1.4, well, what do we get here? Let's see. 760 divided by 1.4, we get 542. So it's only going to be able to go 542 millimeters instead of the 760. the heavier, its density is 1.4 times. It's heavier. So that means it's going to be being pulled towards the Earth by gravity with a greater force than the lighter one. Okay? Or I should say that the force of gravity is being exerted on that, and so it's going to be heavier because it's more dense, and as a result, it's not going to go as high up into this tube due to the same atmospheric pressure. It's only going to go up 542 instead of 760. Okay? Let's see here. Number 10, in a sample of air at exactly 1 atmosphere containing a mixture of nitrogen, oxygen, and CO2. Okay, now they're giving you the partial pressures. Here's the pressure just from the CO2. Here's the pressure just from the nitrogen. What is the partial pressure of oxygen? So notice this is torr, and this is in atmospheres. So we have to change the atmospheres to torr. That is, 1 atmosphere is 760 torr. So that means your total pressure, the pressure in the atmosphere, has to equal all of the total, or the total of the partial pressures. And you know the atmospheric pressure, it's 760. You know the carbon dioxide pressure, 0.323. You know the nitrogen is 593.525. And now you can find the oxygen. So you'll just take 760 and subtract 0.323 and subtract 593.525, and that will give you the partial pressure of the oxygen. Okay? Number 11. The pressure on a gas at negative 73 degrees Celsius is doubled. But its volume is held constant. What will the final temperature be in degrees Celsius? Okay, now in this problem, you'll notice that all we're going to do is use the variables that are given and solve for something that is unknown. Every single gas law problem, that's basically what you're going to be doing. Now, I'm going to show you PV over T, and if you want to put the N in there, that's fine. That's initial, okay? That's the initial situation, and then there's going to be a change. But I want to show you something here. It says here, the volume is held constant. So we don't need volume in this equation. We don't need to worry about it. Okay? And this is a gas, it's in a container, so the number of particles is not going to change. You're not going to increase or add more particles. So really this simplifies. What I'm saying is you can always start with kind of the ideal gas law, okay? This here, and if there's something that doesn't change, then just get rid of it. You don't need it in your equation. This is relating all 4 variables: pressure, volume, temperature, and number of particles. But if something is held constant, as is the case here with volume, then you don't need it in the equation. And number of particles is not changing. So it just simplifies to P over T, before and after, initially and after the change. So all we do now is we plug in the values that we are given here. The pressure on a gas at negative 73 degrees, negative 73 Celsius. Now remember, we have to change that to Kelvin. So negative 73 plus 273, that's how you convert it to Kelvin. You add 273, is going to be 200. That's 200 Kelvin. And it says that the pressure is doubled. Okay, it's not telling you the exact numbers, but you can just put in numbers if you want to, or you could just put a 1 for the pressure, for initial pressure, and then a 2 for the second pressure. That would be fine. So you could say pressure 1 is 1, and then pressure 2 is 2. It doubled. There you go. What will the final temperature be? So the final temperature, here's what we have. We have initial temperature, T1. We have initial pressure is 1. The final pressure is 2. Okay? We plug in those values. 1 over 200 equals 2 over T sub 2. And we solve for T sub 2. So T sub 2 is going to equal 1 over, if I divide both sides by, oh, there, let's do it this way. Let's do the inverse of both of these. Okay, here's one way to solve this. I'm going to flip both of them because T2 is the denominator. So I'm going to have 200 over 1 equals T2 over 2. And then I'm going to multiply both sides by 2 to cancel that. Okay, so I get 400. My new temperature is 400. But be careful, it's asking the temperature in Celsius. So in this case, I would have to subtract 273. And so my new temperature in Celsius is going to be 137 degrees Celsius. Okay? 127, sorry. 127. Okay? 127 degrees Celsius. Number 12, a flask containing 155 cubic centimeters. What is this? This is your volume, cubic centimeters, of hydrogen was collected at 22.5 kilopascals. That is a pressure. What pressure would have been needed to collect the same gas at the same temperature using a flask with a volume of 90? This is your volume. So here's your volume 1. Here's the new volume. There's your pressure 1, and we want to find pressure 2. That's the thing we want to find. Okay? Notice what stays the same. Same temperature and same number of particles. So our PV over NT is going to just reduce. The temperature is not changing. The number of particles is not changing. So this is just showing the relationship between pressure and volume. It's just PV1 equals PV2. And I plug in what I know and solve for what I don't. So pressure, initial pressure is 22.5 kilopascals. And my initial volume is, oops, sorry, I should do this, 155 cubic centimeters. And I'm trying to find this new pressure with this new volume. Okay? So you just divide both sides by 90. Centimeters, cubic centimeters will cancel, and you'll have your new pressure when you take 22.5 times 155 divided by 90, and your answer will be in kilopascals. Okay? You can do that. All right, next one. So a meteorological balloon contains 250 liters. There's your volume. You've got to recognize that as a volume. At 22 degrees Celsius, there's a temperature that we will change to Kelvin, and 740 millimeters of mercury. That is a pressure. You got to recognize that unit. The volume of the balloon can vary according to the external conditions, but it will burst if its volume reaches 400 liters. There is a new volume, probably volume 2. These are all the first situation before it goes up into the air. Okay? At what temperature? What temperature? This is the temperature here that we want to probably find here. There's a question. In degrees Celsius, will the balloon burst if its pressure at that bursting point is 0.475 atmospheres? Here's the second pressure. Okay? So we have a volume 1, a temperature 1, a pressure 1, and then we have a volume 2 and temperature 2 that we need to find, and a pressure 2. It doesn't say anything about changing the number of particles. It's in a balloon. You're not adding or taking away more particles. So N, you don't have to worry about N. So PV over T is what we're doing. 1 and 2. And all you do is you plug in the values that you know, solve for the one that you don't know, which is this T2. So I'm just going to talk you through it, and you can do this calculation. You're going to put in 740 for the pressure. You're going to put in 250 for your volume, and you're going to put in 22 plus 273 for your temperature. Remember, you got to change it to Kelvin. that has to equal pressure. Our new pressure is 0.475, and our new volume is 400. I should put all the units in here, but the units are there. And then we're going to find T sub 2. You solve this for T sub 2 right here. Find T sub 2, and then convert it back. This would be in Kelvin. Convert it back to Celsius by taking and subtracting 273 to get your answer in Celsius. Okay? Convert it back to Celsius. All right, 14. Suppose a 5-liter sample of oxygen at a given temperature and pressure contains this many molecules. Now we're given molecules, we're given moles. Okay? Well, actually, we're given molecules, we'll convert it to moles. How many molecules will be contained in each gas at the same temperature and pressure? Now, I want to mention that volume is directly related to number of particles, moles of particles. Okay? So if you have 5 liters and this many particles, then as the number of particles goes up or down, then the volume is going to go up or down, because your temperature and your pressure are fixed. It says at a given temperature and pressure. Okay? It says how many molecules would be contained in each gas at the same temperature and pressure. The temperature and pressure is not changing. So if you have 5 liters of oxygen and you also have 5 liters of carbon dioxide, they're going to have the same number of particles. Same number of particles. Remember, in our formula, there's no mention of if you had oxygen or carbon dioxide or ammonia or something else. Doesn't matter what gas you have. These gas laws apply to any gas. So if you have 5 liters of carbon dioxide, it would be the same number of particles at 5 liters of oxygen at the same temperature and pressure. So it's 1.08 times 10 to the 23rd. Okay? What if you had 10? Again, it doesn't matter which gas you're talking about. Now your volume doubled, well, then your number of particles would be twice as much. So just take and double the number of particles. Okay? That's it. Number 15. Find the volume in liters of 8 grams of oxygen at STP. Now, we know that 1 mole at STP, remember this is standard temperature and pressure. Standard temperature and pressure means the temperature is 0 degrees Celsius, which is 273 Kelvin, and the pressure is 1 atmosphere. And we know that given that any gas, 1 mole of gas, if it's 1 mole, if N is 1 mole, then we know that the volume has to be 22.4 liters. Okay? Has to be. Any gas. So now, we don't have number of moles, we have grams. So I need to change that 8 grams to moles. Well, the molar mass of O2 is 32. So I'm going to change this. 1 mole of O2 has a mass of 32 grams. Grams are going to cancel. And this is 8 divided by 32, or 1/4, 0.25. So I have 0.25 moles of oxygen. Well, if 1 mole has a volume of 22.4, then 1/4 of a mole is going to have a volume of 1/4 of that. 0.25 moles, and I know that at STP, 1 mole has a volume of 22.4. 1 mole. The moles cancel. You take 1/4 of 22.4, it's going to be about, what, 5 point something, right? 5.6, is that right? Yep. Okay. So 22.4 divided by 4 or times 0.25. Okay. That would be your volume of 1/4 of a mole. All right. All right, number 16 here. Now we're going to be combining some other things. And notice that we used molar mass there in that last problem. So you can't forget that previous information. We have a gas here. It undergoes combustion to produce carbon dioxide and water vapor. And 75 liters of carbon dioxide is produced. So let's balance this equation first. Here's the equation that's happening. Let's start with carbon. I've got 2 carbons on this side, so I need to have 2 carbons on this side. So I put a 2 in front of the CO2 to double the number of carbons. I have 2 hydrogens on the left. I've got 2 hydrogens on the right. Let's check the oxygens. I've got 2 times 2 times 2, that's 4 oxygens, and I got 5. I've got 5, one more there. So that's 5 oxygens. So I'm going to multiply by 5 halves. Why 5 halves? 5 halves times 2, this 2 right here, is 5. But I'm not going to leave that coefficient as a fraction. So I'm going to multiply everything by 2 now. Multiply by 2. I multiply this by 2, cancels that denominator. I multiply this by 2, that becomes a 4. I multiply this by 2. So the coefficients are 2, 5, 4, and 2. Okay? It says find the volume of each reactant and the volume of water produced. Well, it says here that we have 75 liters of carbon dioxide. Okay? 75 liters of carbon dioxide. This is 75. All of these here are going to be gases. They're all gases. And so as the number of moles increases, the volume is going to increase as well. Okay? So if I have 75 liters of carbon dioxide, and that's with 4 moles, then notice the ratio here, 4 to 2. I have half as much water. Half as many moles of water at the same temperature is going to have half the volume. So this is going to be 75 divided by 2. So carbon dioxide has a volume of 75 liters. Water is going to have a volume of half that. Okay? Oxygen reacts in a 5 to 4 ratio. So oxygen is going to be 5/4 times 75 liters. And the carbon of the C2, what is that called? Acetylene. Acetylene gas, right, is C2H2, and that is going to be half. Again, it's a 2 to 4 ratio. Half as much. Okay? All right. So you can do those calculations and find the volumes of each of those. Okay, next one here. I think we got just 3 more. We'll be done. 17. Calculate the pressure exerted by 2.5 liters of hydrogen monofluoride containing 1.35 moles at that temperature. Okay, now here's where we're going to use the ideal gas law. PV equals nRT, or if you want it as PV over NT equals R, doesn't matter. The same formula. Remember, this R is a constant. It's a constant. So we are going to use the R value that is 0.0821 because the volume is in liters, and so that means we'll find our pressure in atmospheres. This is the R value when volume is in liters and the pressure is in atmospheres. All we do is we plug in the values. That's all we do right here. We're going to find pressure. So pressure, I'm going to divide both sides by volume, okay, to get the pressure by itself. nRT over V. All you need to do is you're going to put in 2.50 for the volume right there. You're going to put in 1.35 for the N, the number of moles. You're going to put in 0.0821 for your R. And you're going to put in, it's already in Kelvin, how nice of them. Put in your temperature and solve for pressure, and the atmospheres will be your units. Okay? Number 18. Excuse me. Determine the number of moles. Anytime you see moles, you're going to use PV equals nRT. okay, in 1.25 liters of gas at that temperature and that atmosphere. Same thing, PV equals nRT. And notice it's liters and atmospheres, so our R value is the 0.081 or 0.0821. Your volume is the 1.25 liters. Your temperature is already in Kelvin, very nice of them, 250 Kelvin. And your pressure is 1.06 atmospheres. I'm going to let you do this one. Put in everything that you know. You know the pressure, volume, you know the R, the T, and solve for the number of moles. Okay? All right, compare the rates of effusion for fluorine and chlorine. So all we have to do here is rates of effusion, the rate of fluorine and the rate of chlorine is going to be equal to, that ratio is equal to the square root of the mass of chlorine over the square root of the mass of fluorine. Okay? So you look on the periodic table. I'm going to let you do this. You got to have your periodic table. Take mass of the chlorine. Find the mass, the molar mass of chlorine. Take the square root of that number over the square root of the mass of the fluorine from the periodic table. Take the square root of those two masses, divide them, and you're going to get a value here, a ratio. Now, listen for a second. This number that you get, let's say fluorine and chlorine. Chlorine is heavier. Let me just do something really quick here, and we'll check it. All right. Okay, the periodic table. Look at the periodic table, and you'll find that the mass of chlorine is around 35, 36, 35.5. So I'm just going to estimate here. Let's say that it's around 36. Okay. The mass of fluorine is around 19. All right. So right here, you take the square root of 36, which is 6. So it's approximately 6. The square root of 19, well, the square root of 16 is 4. The square root of 25 is 5, so it's in between that. So it's going to be 4 point something. All right. 4 point something. You are going to find and evaluate this. This is going to be close to, 3 halves. It's close to 1.5. I don't know. I'm just estimating, just doing some mental math here. So let's say it's approximately 1.5. All right. What does that mean? Make sure you understand what this means. It means the rate of fluorine. That's the lighter one. Lighter. According to the periodic table. It's down here. It's lighter. This is the heavier one. The lighter one is going to travel 1.5, approximately 1.5 faster, 1.5 times faster than the heavier chlorine. Okay? And that's how you compare them. Notice you're not finding the actual rate. You're not finding the number for each rate. You're just comparing them by finding the ratio of them. Okay? All right, great job. I hope this was very helpful, showing you all the calculations. A lot of calculations in this chapter, so make sure that you do them on your own and you practice. There are lots of examples in the text as well, so go back and look at those and follow those examples. And as always, contact me if you've got questions. All right, great job. Let's keep working hard.